So we are ready to start the last session of this morning. And this session will have 4 speakers. And I invite the speaker to speak into this microphone for those who follow from home, and to stay within the 20 minutes, questions included. And so I think we can start with the first speaker, which we have here, is Yuma Kasai from Shizuoka University, Japan. And he will talk about performance and prediction of a household water purification filter. Please.
Hello, everyone. I'm Yuma Kasai from Shizuoka University, PhD student. Thank you very much for your kind introduction. Today, I'll talk about the performance prediction of the water purifier by OpenFOAM. First, I'll talk about the background of this study. There exists numerous types of water purifier, water purification filters, such as water purifier at home. The water purifier is equipped with the cartridge. The cartridge removes the impurities. Cartridge's material is activated carbon, zeolite, and so on. Also, the cartridge's lifespan is several months to several years, and so the filtration performance of cartridge prediction requires a long-term experiment. And this long-term experiment is high cost. So we try the long-term prediction of cartridge performance by CFD. And next, I'll talk about the dominant factor of filtration performance. The dominant factor are flow field and calculation field. First, I talk about the flow field. The filter is treated as a porous media. The flow field includes the porous media occurs a pressure drop. This pressure drop is represented by Darcy's law. Darcy's law is represented by this equation, and this equation shows that a pressure drop is proportional to the flow velocity, and proportional coefficient D is Darcy number. We need the estimation that Darcy number to predict the flow field. But the estimation of Darcy number requires a very simple flow test. This simple flow test is a measurement of the relationship between the flow velocity and pressure drop. Next, I'll talk about the concentration field. The concentration field dominant factor is adsorption rate. Adsorption rate is impurities adsorption amount per unit time for filter. And adsorption rate is represented by LDF model as shown this equation. This equation shows that adsorption rate dQ dt is proportional to the concentration difference between the Qmax Kc and the Q. And the primary determinant of adsorption rate is the adsorption rate parameters. Adsorption rate parameters as mass transfer capacity coefficient Ka and adsorption constant Qmax K. The mass transfer capacity coefficient is a proportional constant, and adsorption represents the maximum concentration. So this equation shows that dQ dt is proportional to the concentration difference between the maximum concentration and concentration at any given time Q. But the estimation of adsorption rate parameters requires a series of experiments involving the adsorbent amount or solution concentration. So this experiment is high cost. Next, I'll talk about the object of this study. Final object of our final final purpose is long-term prediction of filter performance. To predict the filter performance, first, we try the prediction of adsorption rate parameters by CFD. And we perform the iterative concentration field calculation until the calculation result fits to experimental result. From this fitting result, we obtain the new adsorption rate parameters. Next, to evaluate the predicted adsorption rate, we perform the prediction of adsorption performance of actual shape filter of water purifier. And from this prediction result, we evaluate the concentration distribution inside the filter, and we apply this result for filter design. I'm going to talk about the method of this study. First of the evaluation condition, and adsorbent is a granular activated carbon used for water purifier. And the solution is a filtrated water. And impurity is a chloroform. It is generated by reacting residual chlorine and organic matter. Also, it is an important substance for water purifier design. And other conditions are shown in this slide. Also, we perform the experiment based on this standard. It is a Japanese standard of water purifier evaluation. And we perform the calculation by using OpenFOAM. And calculation model is two-dimensional axially symmetric model to reduce the computational cost. I'm going to talk about the calculation detail. First, I talk about the flow field calculation. We perform the calculation of the flow field using the Darcy's law as shown this equation last time. The Darcy number is measured by advanced experiment. Here, the chloroform adsorption does not change the filter structure, so Darcy number is constant and the flow field is steady state. So we use the simple form, and the Darcy number is set up for FV options as the porous media condition. This is a concentration field calculation. In the concentration field calculation, we use the transport equation as shown at this upper equation, and including the adsorption rate term last term of this equation. To solve this equation, we use the scalar transport form, and this equation is customized. And we define the new parameter as shown this slide, including the adsorption parameters, mass transfer capacity coefficient Ka, and adsorption constant Qmax K. This is the result. First, I talk about the adsorption rate prediction. This graph shows the relationship between the sedimentation amount of impurities and the total flow volume. The sedimentation amount is represented by this equation, and this red dot line shows the experimental result, and these green lines show calculation result. To predict the adsorption rate, we perform the iterative calculation until the calculation result fit to experimental result, as shown this green solid line. From this result, we obtain the new adsorption rate, Ka and Qmax K. In this result, adsorption rate parameters Ka is large and Qmax K is small compared with the initial condition. From this result, we can reproduce the experimental result. But this is a result for a very simple filter as shown this figure. So to evaluate the accuracy of predicted adsorption rate, we perform the actual shape filter performance prediction. And this slide shows the actual shape filter condition, and the left side figure shows the actual shape filter construction. This is a very simplest the filter of water purifier cartridge. The water flow from the inlet to outlet pipe and the center of filter through the adsorbent outside the adsorbent. And other condition shows shown in this slide, and calculation is performed by OpenFOAM, and the calculation model is a two-dimensional auxiliary symmetric model. This is a result of adsorption performance of the actual shape filter. As a result, this graph shows a breakthrough curve. A breakthrough curve represents the concentration ratio outlet for inlet time change. Here, in this study, inlet concentration is constant. So this graph shows the time change of the outlet concentration. This red cross mark shows the experimental result, and this black dashed line shows a calculation result using the predicted adsorption rate. And this calculation result is good agreement with the experimental result. So we concluded the predicted adsorption rate parameter is applicable. Also, the filter's lifespan is time when the concentration ratio reach at 0.2. In this result, we can reproduce the cartridge's lifespan. Also, flow field is steady calculation, and concentration field unsteady calculation. So we can perform the long-term prediction. And we can measure the concentration inlet and outlet, only inlet and outlet by experiment. Also, by using CFD, we can visualize the filter inside the filter. So we can obtain the local concentration distribution by the CFD. This solid line shows a local concentration distribution at each local point inside the outlet channel. Y equals 70 millimeters, Y equals 31 millimeters, Y equals 5 millimeters. We call this local concentration distribution local breakthrough curve, and we define the generally breakthrough curve as the global breakthrough curve. We consider we can apply this local concentration distribution for filter design because we can visualize inside the filter. This is a discussion. The adsorption packed bed is divided to 3 zones: a saturated zone, adsorption zone, fresh zone. In the saturated zone, the adsorption is finished. In the adsorption zone, the impurities are being adsorbed. In the fresh zone, adsorption has not yet started. Here, the experimentally methodology can measure only at inlet and outlet or for concentration. However, the CFD can capture the effect of adsorption zone effect as shown in these figures. And so we concluded the predicted performance by this method becomes high accuracy. And CFD, we can apply the CFD for filter design because CFD can reduce the trial and experimentally trial and error. So we can apply the filter for filter design. This is a conclusion. Thank you very much for your kind attention. For Heimer coefficient, this for this very flow speed is very low, so no we can consider no flow Horkheimer.
Thank you. So good morning all. Thanks for coming, even though this is the last session for today, technical session. My name is Tejaswi. I am from TU Darmstadt, working at the Institute for Technical Thermodynamics with Professor Stefan. The title of the talk is Transport and Absorption Kinetics of Surfactants within the algebraic VOF method. This is a project sponsored by DFG, German Science Foundation, where we have an active collaboration with the industrial partner Heidelberger Druckmaschinen, where they do the experimental part of the simulations that we try to validate. The basic outline of the talk is I want to introduce what is a surfactant transport in VOF, especially algebraic VOF, and why it is both interesting and challenging, followed by the absorption kinetics, meaning adsorption and desorption kinetics at a liquid gas interface, where the methodology and validation will be presented, followed by the similar methodology and validation now for a solid liquid interface. Then the application of this methodology and our overall code that we have developed for a problem of impact of a drop on a substrate. And I would like to also say that the first part, where the absorption kinetics at a liquid gas interface, the methodology is mostly developed by a PhD candidate, Thomas Antrater, who recently graduated, followed by which I am working as a postdoc in the lab. Then to start with the problem, the simulation of surfactant influenced flows. Basically, first surfactants are, as you know, most of you, molecules which have hydrophilic and hydrophobic ends. They basically adsorb, meaning they get accumulated at an interface, which can be either liquid gas or solid liquid interface. They tend to reduce surface energy. So most of the times when we need better wetting of a surfactant solution, people use surfactants there. And this is a typical example curve of a surface tension. This is basically a dynamic surface tension where the surface tension decreases with the time at a particular liquid gas interface due to adsorption of surfactant. Then the second thing is the method, which is VOF, and especially algebraic VOF, where we use algebraic formulation to advect the interface and also the reconstruction, but not as geometric reconstruction. And here we have one additional scalar transport equation, which the scalar identifies the volume fraction in a particular computational domain or a cell. And when this scalar is 1, we can say that it is in phase 1, 100% of volume fraction. And if it is 0, it is phase 2. In this particular study, we consider alpha 1 as liquid and alpha 2 as gas, so that within alpha 0 to 1, we have an interface region. The advantage of algebraic VOF is that we don't have a surface mesh. Therefore, any topological changes occurs, we don't have to remesh. But of course, if you want a faster simulation, we might need AMR grid refinement. But in principle, we don't need a remeshing whenever there is a change. For example, here in impact and collision of a drop on an already sessile drop is shown here. Then the idea is, how do we relate these two aspects? Because as I talked about, surfactants are basically surface dominant phenomenon, meaning whatever adsorption or even the phenomena of transport can be wholly identified by a quantity which is at the surface, means per unit area. Whereas in volume of fluid, if you want to solve mostly a scalar transport equation or even any field, it is per volume. So somehow we need to have a connection between these two. That is where the next thing comes when we start with the absorption kinetics at a liquid gas interface. So Gibbs adsorption equation is the equation which relates the gamma, meaning surface excess concentration per unit area, with the surface tension at a point and the bulk concentration of surfactant at that point. Now there is this continuum surface transport, which is well developed before, which transfers a variable or even a field which is per unit area to per unit volume. where we can multiply that with an interface regular delta function. As you can see here, for a distribution of alpha on the left side, where you can see an interface where alpha changes from 0 to 1, you can define a CI, which is concentration at the interface, which is basically multiplication of the regular as a delta function and then the gamma, which is in parameter square. So by doing this, we get the concentration of surfactant, which is at the interface only in the interfacial region. Then coming to the numerical methodology, as you all know, mass conservation equation consists of both the scalar advection equation for the volume of fluid combined with the continuity equation, followed by the momentum equation with all the regular terms and the body force term, which is also in the interfacial forces term. Here we have dominantly the surface tension force, but also in some cases, if needed, a collision force or wall contact force, all these can be implemented. Then the interesting methodology, especially for the surfactant, which is soluble, meaning that the surfactant concentration in the bulk and also at the interface have to be tracked. So we have a two-field formulation, CB, which is the concentration in the bulk, and then whatever surfactant is absorbing at the interface can be defined by CI, as I showed before. And then within the liquid phase, then we have a volume average concentration, which can be defined as C1. Then to consider the adsorption or desorption, we have a source term JB or JI for the interface and the adsorption, which can be identified with any adsorption model coming from either experimental measurements or any numerical model that you fit, just like the previous presentation we saw. We get experimental validation, and then you can fit an adsorption model based on which we can calculate these source terms. Now, as I said, this source term is basically dependent on surface concentration at the area, at the interface per area. So we have to somehow connect it to Ci and gamma, as I showed before. But the reverse is not that easy, meaning once you solve this transport equation, which is mentioned here, Ci, and you have a liquid fraction alpha, you get a Ci field, you get a delta, which is basically norm of this alpha. But if you directly divide these two to get gamma, it will be numerically very difficult because both are defined in a very small region of the interface. So by using this advection diffusion equation, we can smooth these fields using a small kernel, diffusion kernel, which will conserve, but it will have its own issue because of the time step and the Coron number. But by making it mesh independent, we can slightly smooth these values. And then once we define and then divide those things, we can get surface excess concentration per unit area, which is where most of the adsorption models and then the source term is defined. Now, once we have that source term defined, we can get again the transfer of this specific source term to volumetric source term, as I showed before, using continuum surface transport. Just like how we multiplied gamma with regularized delta function to get Ci, we can multiply the rate of adsorption with this J gamma here with the regularized delta function to get the volumetric source term. This will directly go into the transport equation for this C bulk and also Ci. Then such an example is shown here where a liquid drop can be seen, although this is an axisymmetric case. And with the particular alpha field that is shown here, once we have the source term Ji, which is only defined at the interface, we can see this distribution. And again, following the similar methodology that I have shown before to diffuse the Ci field, which is very narrow region at the interface, we can again do this diffusion. But in this case, we have to be careful that this source term has to be diffused only inside the drop. Means it has to be defined into the drop because that is where Cb exists. So accordingly, by using this formulation, we can smooth it so that we have the JB defined all over the region. This is basically the methodology where we have two fields and then they are coupled using the adsorption and desorption. Now, coming to the validation of this, consider a axisymmetric case where we have a spherical drop, and this maroon or something color is where the bulk concentration is constant at the initial time. And then at the interface, you have zero surface excess concentration. But with the time, according to the adsorption kinetics that I have shown here, so this term dou gamma by dou T is basically the source term per surface area. This will define the adsorption kinetics. And then with the time, you can see that the bulk concentration decreases within the drop. And at the same time, because of this, there is an adsorption at the interface happening, and then gamma will increase. This is a non-dimensional time according to this analytical solution, which is also incidentally from our Department Technical University of Darmstadt from another group. And also this comparison of the same with respect to quantitative values of concentration within the bulk it shows very good validation because the adsorption kinetics and also the model is pretty linear with the bulk concentration. So that concludes the part of adsorption kinetics for the liquid gas. And now coming to the next part, taking this model to the next level of having same kinetics for a solid liquid interface. Again, the bulk concentration transport equation is mentioned here, which is very similar to the previous case. But now any solid liquid interface can be basically from numerical methodology can be considered as a wall. So for dealing this adsorption at a wall, we have to have a specialized boundary condition for the same. So that is what it is mentioned here, where the overall fluxes diffusion to the wall should be equal to the rate of adsorption at that point, which is straightforward. Then once we implement that extra field gamma S, meaning the surface excess concentration at the wall or even a solid liquid interface, we can see that the bulk concentration within the drop decreases and the concentration of surfactant at the wall increases with time because of implementing this custom boundary condition. But here you can see an issue straight away that this works only when the drop is stationary. When the drop moves, there might be surfactant which is not previously the liquid surface, meaning there might be surfactant away from the drop, and once it moves, somehow you have to take care of that also. That is where you have to implement more data into this boundary condition. That is what is mentioned here. So when we have a receding contact line, then we don't have any issue because it is already a liquid and then you already have a wetting region there. Then you can directly consider whatever is the adsorption rate, you can directly consider this and to get the overall concentration. Whereas if you have an advancing contact line, as I said, if there is any concentration that is there, you have to consider that also. So therefore, because of this, you have more complication where you have to track two different fields now, that is concentration at the solid liquid interface and also concentration at the solid gas interface. Therefore, this overall boundary condition can now help us deal with this adsorption at a wall when even there is an advancing or receding contact line. And then finally, the overall concentration is related to these fields like this. This is straightforward because when alpha equals to 1, that means it is in the liquid phase, and alpha equals 0, it is in the gas phase. And within the interfacial region, you calculate using the weighted formula. Now, this is the small animation where such an implementation has been shown for an advancing contact line. Now, once we make sure that this works, so for the liquid gas interface, the overall methodology is about how we treat the source terms at the interface. And for a solid liquid interface, it's all about a custom boundary condition. That's what it boils down to. And just for the interest of this audience, this boundary condition at the wall, as I mentioned, is implemented using mixed boundary condition. And just to be mentioning here, all this is developed in the InterFOAM solver. And then we extended it using different libraries for contact line dynamics, adsorption dynamics, and everything. It's an open source library that we are going to publish. And using this mixed boundary condition, in the OpenFOAM, we have modified our boundary condition. For example, as I said, the net diffusion should be equal to the rate of adsorption. Then once we do some mathematical manipulation, we can arrive at the final expression where the bulk concentration boundary condition at the phase will be defined by a fraction and then the gradient. This is very similar to the development of mixed boundary condition. And according to the rate of adsorption, which again, as I mentioned before, can be from any adsorption model that can be de-linked. So in that fashion, this is a very modular implementation where this JSL, this is the adsorption rate, that can be calculated from any adsorption model you have. And then you can finally implement the same boundary condition for your solver. Then for the same methodology, here I show the validation for this. And since we can increase the complexity, we have taken a 2D case as opposed to the axisymmetric case before. And you have a domain where 2/3 of the domain is filled with liquid and then 1/3 is gas. And within the liquid, you have a fixed surfactant concentration in the bulk. And then initially at the solid liquid interface, there is no surfactant, which is shown here in the red color. And then right now, the liquid gas interface, there is no adsorption, so that we can consider only the adsorption. It's like a one-dimensional phenomena because the bulk concentration on the other end, on the left here, is fixed. So that we can assume that all the concentration of surfactant will move towards wall and there is an adsorption happening there. So for this, the properties of ethanol water solution were used. These are well defined in literature. And one interesting phenomena why we use this is that this has a mixed adsorption kinetics, meaning for some time the adsorption is limited by the diffusion and sometimes it is limited by the adsorption. Meaning there is two phenomena happening here. The surfactant within the bulk has to diffuse towards the wall and then get adsorbed. So any of these two mechanisms can be limitation. Accordingly, by using a adsorption model like Langmuir-Freundlich kinetics, we can simulate the ideal cases of adsorption limited, diffusion limited, or also mixed kinetics. So such a validation is shown here. Just excuse me, I think it will take some time to come back again. So this is just a 3D representation of the 2D case. And as you can see here, so yeah, with the time, the concentration at the wall increases. And because of this, the surfactant in the bulk decreases. But since the other side, the bulk concentration is fixed, slowly it gets replenished. And again, the system comes back to the original position. And as I said before, these are the snapshots. And then you can see here that in the initial stage, even if you forget about the time scale for this problem, we can see that it is adsorption limited, meaning the bulk concentration is almost constant, as you can see here. But later in the stages, it will transport to diffusion limited, and that is where you can see some gradient in the bulk. Then it was compared with well-known numerical solution in both cases. As I said, one adsorption limited, one diffusion limited, and also mixed kinetics. And in all cases, we could see good validation. Then finally, the application of this and the reason why we have been developing this is that, as I said, with our collaboration with Heidelberger, where we want to see an impact of a drop, which is filled with surfactants onto a substrate, which is very relevant in inkjet printing. There, for example, as you can see here in the shape S, you have multiple drops and then they coalesce, and also there are so many interactions with the substrate and also with other drops. So this is the domain. It's an axisymmetric domain where you have a drop and then there is a surfactant inside the drop. And initially at the interface, there is no surfactant, and then it comes and impinges onto the wall. So one important thing, as you might guess, is the contact line dynamics, which are very important here. I'll not go into the details, but we used a subscript scale model of Kizar dynamic contact angle. And the adsorption parameters are from experimental characterizations for that particular surfactant. But just boiling down the story is that, yes, you have a case where the drop comes, impacts, and then it spreads. And particularly this case is for a very small drops, meaning the volume is around picoliters and the drop diameter is around 20 microns. So that poses so many challenges on the inertial scale level, where sometimes the drop doesn't even have enough to come. So we do it with very high velocities, which is similar to what inkjet printing people observe. And you can see that during the process, it spreads. There are many phases, but more importantly, the surfactant adsorbs at both interfaces here. So that is where all the formulation that I presented before can be used here. And the impact kinetics, just to show you that, how the spread radius varies. There are different phases like impact driven, relaxation, and then finally adsorption driven, meaning the surfactant takes some time for the adsorption to happen at the liquid gas interface. And then you have different phases of spread. And then, yes, that is the conclusion where we have developed a methodology in OpenFOAM 4x, especially using interfoam, and then we extended with different libraries of contact line library and adsorption dynamics with custom boundary conditions, and also at the interface, how to deal with source terms which are defined in a very small regions. These methods have been developed before, but we implemented that for the surfactant transport with 2 fields. And then this has been verified and validated with both liquid gas and solid liquid phases. And then although we started validating, and then we are still looking into more details of this inkjet printing phenomena. Then finally, the more important part, acknowledgements. We gratefully acknowledge the support from German Science Foundation. This is a collaborative research center where 3-4 institutes are involved. And this project especially is from sub-project T01, where there is a transfer between industry and academics. As Heidelberger Drug Maschinen, based out of Heidelberger, they help us with all the experimental characterizations. Although I haven't shown the actual experimental validation here, but I want to acknowledge them. And then the high-speed computing cluster at TU Darmstadt. And also more importantly, the basic methodology of the codes and also this methodology is from within the different departments within TFI of TU Darmstadt, from where I come from. That's it. Thank you. Yeah, so the initial contact line library that we developed was from there. And then when we ported it to OpenFOAM 6 or even 7, we were having some issues. And most importantly, the AMR, the grid refinement that we were using, is slightly out of date. So, but now we are already porting that library to the newer versions. Yeah, so yeah, that's very interesting. So strictly speaking, it should be much easier there, because you have a surface mesh and you know all these things, it will be easier. But the problem is you cannot define very short regions, just like at the interface, you can define this gamma and all. The advection will be easier, but we can directly shift the entire thing there. In fact, we have been already doing that. It will be much easier there. But as you know, like it takes more time and to construct all these things in geometry, we were sticking to algebraic form.
Okay, thank you, Mr. Chairman.
I'm Pratyush Kumar from IIT Bombay. So today I'm presenting the talk on the modeling of heat transfer, including radiation of the binary packed bed. So you might be seeing this as a binary backed bed on Hua app. That is typo error. Sorry for that. So I did this project under the guidance of the Professor Sandeep Saha and Professor Atul Sharma from IIT Bombay. So let's begin the talk. So first of all, I would like to thank you to Namaste to all of you from India. So this is the outline of my talk. So I will start with the introduction, then objective. Then I will talk about the mathematical model and of course the numerical methodology, then result and discussion, and finally conclusion and future scope. So first let's begin with the introduction section. So first let me talk about what is the binary packed bed. So mono-sized packed bed is filled with the one kind of particle. So you can see the different parameters on the left side that is related to the mono-sized packed bed. But speaking of the binary packed bed, there are two different kinds of particles filled in a given box or given cylinder. So there are two important parameters, that is the volume fraction of large particles and the size ratio. So here I am tuning these two parameters, that is the volume VFL and the size ratio, and studying the parametric study on the heat transfer effect. So why this binary packed bed is important? So because it has a many applications, like in fluidized bed, catalytic bed, and nuclear reactor, this binary packed bed is generally used. But my focus is on this, that is a tritium bleeding blanket. So I think most of you heard about the ITR experiment that is being performed by the many countries. So like India is participating, European countries is also participating, France, China, these countries are participating to stabilize the nuclear fusion reactor. So why this binary packed bed is being used? Because it has the many advantages, like the higher packing fraction, larger thermal conductivity, and of course the effective heat transfer. So this slide, can you relate you that what is the breeding blanket? So this is the experiment that is being planned, and it is known as the ITR experiment. So here, this is the breeding blanket zone. So this nuclear fusion reactor that is ITR is planning, it uses two fuel, that is the deuterium and tritium. So this deuterium can be found in the sea, but for tritium, they are planning to build up a breeding blanket, and it has many objectives. So two objectives is the temperature uniformity and the heat extraction behavior of the binary breeding blanket should be enhanced. So I am focusing only the heat transfer aspect in this project. So with this introduction, I can now define my objective. So first I have developed the heat transfer modeling for the purge gas. So purge gas is going through the packed bed, and it is purging out the heat transfer, and also it is purging out the tritium. So that heat transfer model I have developed here, and also CFD-DEM methodology for the binary packed bed using completely open source. So generally I found that so there is three process for the CFD-DEM methodology, starting from the DEM simulation, then geometry creation, and then meshing. So out of these three processes, generally I found that one or two, they have depend on the commercial software. But in this project, I have just used everything open source software. Then after that, I have done the parametric study, that is the effect of the different size ratio, and of course the effect of the initial pebble temperature. So remember that there is two parameters, that is the size ratio and the volume fraction of the large particle. So here I am fixing the volume fraction of large particle, and I am varying the size ratio only. So let's talk about the mathematical model. So I am just modifying the simple form. So simple form that UE equation and PE equation, I have not done any modification. For energy equation, I am solving two equations, one for the fluid and one for the pebbles particle. Now here I cannot ignore the radiation because the temperature is very high. So radiation we have to consider. So to model the radiation, there are two approaches generally used in the literature. So one is known as the fourth order radiative transfer equation. It has advantage that it is very accurate model, but it is computationally expensive. Now second approach is the effective conduction approach that is computationally economical, but also it also approximates the behavior. Now my focus is on the study the behavior of the purge gas flowing through the packed bed. That's why I chosen the second approach. And also it is of course computationally economical, so it is better option. Now what is the second approach? So here to model the radiation, this is the equation I can approximate. So radiation heat flux I am approximating using this K equivalent radiation. And to model this K equivalent radiation, there is a JBS model. And I have used this empirical correlation in one of my first paper. And this K radiation plus the K of the solid pebbles, I can equate equal to K equivalent of the pebble particles. So this is the approach to model the radiation heat transfer. So let's discuss about the numerical methodology. So I use the LIGHTS software that is open source for the DEM simulation. And then after the simulation, I exported the location of each particle as a CSV file. And this free CAD is the CAD modular where I have written Python script, and using that Python script, I have generated the geometry. And after generating the geometry, I use the snappy hex mesh for the mesh generation. And for solving the CFD simulation, I use the OpenFOAM. Of course, I need to modify the simple form because I had to introduce the heat transfer with the radiation. So this is the simulation setup, and this is the DEM simulation parameter. So remember here that I am fixing the volume fraction of the large particle. Now this is the one test case I am showing for the size ratio 3. So here DEM simulation you can see, and this is the geometry after using the free CAD, and this is the complete CFD simulation mesh generation. So this is the modification that I have done in simple form. So I am keeping the UE equation, P equation as it. I modified the temperature equation for the fluid, and for the each pebbles at a walls, I have applied this boundary condition. You can see that I am equating K equivalent equal to K radiation plus KSI. Okay, so I am also keeping track of the pebble wall temperature to update the temperature, update the physical properties of the pebble particles. So this is the, now I can talk about the result and decision. So of course, this is the, all the pebbles, all the different binary packed beds for different size ratio. And before going to the analysis part, I need to validate the model, that is a DEM model, and of course the heat transfer model. So this is the validation. I have validated the porosity from center towards the wall using the de Klerk correlation, which is a very famous correlation for the mono-sized packed bed. And for the heat transfer model, I have validated the experimental result of the Yagi and Wakao. And this is the experimental setup of this Yagi and Wakao. You can see here that there are deviation because to mesh the binary size packed bed, to mesh the packed bed, I have shrinked the particle size because to avoid the skewness between the particle gaps. So this is the technique that is generally used in many literature to mesh the packed bed. So this is the reason why you can see the deviation here. Now to compare the value of the temperature for different packed bed, I have used this quantity. So if this quantity approaches to 0, it signifies that there is uniformity in the packed bed, and the heat extraction behavior is improved. But you can see that it is hard to compare here. That is why I have taken arithmetic average of this T star quantity, and I have plotted this quantity. And of course, one of the objectives is to extract the heat transfer from the breeder blanket. So to compare the heat extraction behavior, I have plotted the Nusselt number. And this dp, this equivalent particle diameter, I have used this this correlation, which is from the Bejan book. And you can see that this is a plot. So here I'm comparing the T star. So we can see from the T star that the fraction of pebble particles at higher temperature decreases with the increase in the size ratio, which is because of the cumulative effects of the deeper penetration, because at higher size ratio, the particle is densely packed. And this T star is also representing the uniformity. So as the T star is decreasing, so it means that uniformity is higher at given same condition for the higher size ratio packed bed. And why the reason is that fluid flow complexity increases, because at higher size ratio, the packing of the packed bed is very complex. And due to this complexity, the fluid are mixing together very well. And that is why it enhances the heat transfer. And from the Nusselt wall, you can see that near the side wall, heat transfer also increases with increasing the size ratio. And also I compare the different initial wall boundary condition. And I found that if the initial pebble wall temperature is higher, the uniformity is greater. So which is because at higher temperature, radiation is more significant. So with this, I can conclude here. So I have developed the CFD-DEM methodology using the completely open source. And also I have introduced the heat transfer model for a purge gas flowing through a packed bed, which is the based on the effective thermal conduction approximation. And the resultant discussion, we found that the higher size ratio enhanced the heat transfer, and also it enhanced the heat extraction behavior from the side walls. Also, it increased the Nusselt numbers, indicating that heat transfer behavior is improved with increasing size ratio. And this is the pictorial conclusion we can see here that. And the future scope that CFD-DEM methodology can be utilized for other packed bed applications. And also we can conduct heat transfer study to understand the complex behavior of the packed bed in more details for the binary packed beds. So with this is my references, and thank you to all of you. So I did DM simulation to get the location of each particle. From that I have exported as CSV file. Then I use the CAD modular, that is the free CAD, to generate the geometry. And then that geometry as a STL file, I'll export it in the OpenFOAM to do the meshing. Yeah, so there is one paper in the references. So I think, okay, so I have not written the, so there is a one method technique that is called as shrinkaging the particle. So we generally shrinkage the particle that is the 0.98 of the particle diameter. And with this, we can avoid the contact points between the pebbles. No. So that is why you are getting some error in the heat transfer. Yeah. Yeah, so we have a number of particles. Yeah. Yes, sir. So I was trying to modify the snappy hex means coding from SRC level. So from there I wanted to just read the CSV file and then create the spherical kind of particles, and then I'll let automatic generate the meshing. But I was not able to succeed in that method. So Nusselt number, I have taken the K value and this particle diameter, and the equation I've shown that I have just plotted, taking the average of all the side walls. Area average, I have taken the area average for the different size ratio backed bed, and I have just plotted. There is only one number for a given size ratio. Yeah, so means you have to do means like CFD-DEM coupling. I think some. Yeah, that is the difference. Means my study was just a parametric study, so I have just fixed the particle location. Sorry? I could not hear. See, the breeder blanket is means this is not the actual test case of the breeder blanket. So actually that is different. I am just means studying the effect of the different parametric study.